So we'll discuss our sixth primitive affine transform, which is permutation. So to understand this transform, let's look at an example. For I equals 0 to n, for j equals 0 to m, zij equals zi minus 1 j. So notice that in this example, we are accessing a two-dimensional array indexed by two indices, I comma j in this case, and I minus 1 comma j in this case. And so, you can see that it's not the innermost dimension which is, which has a dependency. It's the outer dimension which has a dependency. Within the statement, there's a dependency from I comma jth iteration to I minus 1 comma jth iteration, because in the I minus 1 comma jth iteration, zi minus 1 comma j would be written, and in I comma jth iteration, zi minus 1 j would be read. If I was to basically draw the pictorial representation in 2D, and I draw the inner dimension as the x-axis, so the inner dimension is j, and the outer dimension as the y-axis, which is I, and so the lexicographic order is basically shown by these green lines. So first I exhaust all values of j for the first value of I, then I exhaust all values of j for the second value of I, and so on. Then the dependency edges are drawn in gray. For example, there is a dependency from 0, 0 to 1, 0, right? Where this is I comma j, so I is coming first. So there's a dependency from 0, 0 to 1, 0, and this is exactly what our data dependence constraints would also have told us, because as I said before, in our 1, 0th iteration, 0, 0th element would have been read because of this I minus 1 comma j, and in the 0, 0th iteration, 1, 0, 0 would have been written. So in 0, 0 iteration, z00 would have been written, and in 1, 0 iteration, z00 would have been read. And so there is a read after write dependency as shown by this gray edge. And in fact, this can be generalized to 1, 1 and 2, 1, 0 and 2, 0, 1, 2, 0 and 3, 0, and so on, and similarly for other values of j. Okay, so this is our dependency graph, and we can see that the outer loop iterations, which are the iterations of I, are not data independent. They are data dependent, because this is the lowest bottom row is basically for when I equals 0. And then the second row is basically when I equals 1. However, I cannot execute the iteration for I equals 0 in parallel with the iteration for I equals 1, because there are data dependencies between the iterations of I equals 0 and the iterations of I equals 1. So there is no data dependency between, there is data dependency between different iterations of the outer loop, and so the outer loop is not parallelizable. Now it's a different matter that the inner loop for a given value of I, for a given value of I, the inner loop may be parallelizable, but that is, that's like saying that the outer loop is not parallelizable, and the inner loop doesn't have that much parallelism to have, because inner loop only contains one iteration per point, and so the inner loop's parallelization is not going to be very helpful if the outer loop is basically sequential. So we are going to basically transform this program so that we can have better parallelism, and we are going to use our well-known technique of space partitioning constraints. So what is the first step in doing so? We are going to represent this program as a polyhedron, as a set of polyhedral constraints. There's only one statement here, which is zij equals zi minus 1 j. I mean, there are actually two static axes, but they basically have a dependency, so we're going to consider this as one statement. And so this statement has an iteration space of two-dimensional iteration space formed by the Cartesian product of 0, n, which is for I, and 0, m, which is for j. So for example, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, all the way till n. So there are m plus 1 into n plus 1 kind of elements in my iteration space, and now I basically want to set up the data dependence space partitioning constraints. And so basically I want to say that whenever there are two iterations that have a data dependence, then it must be true that they are mapped to the same processor. And so this is what our data dependence constraints would look like. Let's say one of the iterations in points in the iteration space is I comma j, and let's say the other point is I prime comma j prime. Then for there to be a dependence between I comma j and I prime comma j prime, it must be true that, if I look at these two static accesses, then the two iterations should access the same location. And so in other words, the location accessed by I comma j as a write would be I comma j, z I comma j, and the location accessed by I prime, the I prime comma j prime iteration is z I prime minus 1 j prime. So for there to be a data dependency, it must be true that I comma j equals I prime minus 1 comma j prime. And notice that I'm only considering data dependence, I'm only considering this axis and this axis as a pair. I could have also considered this axis with itself, in which case I would have said that there is no data dependency because every iteration is accessing a different element of the matrix. Similarly, I could have looked for data dependencies for this axis with itself. Once again, I would have found that they are all data independent. So the only data dependencies are across this axis, and that's what I have encoded in my space partitioning constraints. So when I comma j equals I prime minus 1 comma j prime, then it must be true that they map to the same processor. In other words, the function from p from I comma j for this statement should be equal to the function from, maybe I should say p prime for the different function from I prime minus 1 comma j prime. Now actually it's p prime should be equal to p because it's the same C statement, right? So there are anyway kind of static data dependencies. So P prime would be equal to P, and so I can just say P. Now when I look for the maximum rank solution for this function P, which needs to be an affine function in our framework, then I just get this solution that P must be equal to J. So notice that because there are dependency chains for I, so for example, there's a dependency from 0 comma j to 1 comma j, 1 comma j to 2 comma j, 2 comma j. So along the dimension of I, everything is data dependent, but along the dimension of j, things are independent, and that's what we also saw in our pictorial representation. And so basically what I'm saying is that just partition the space such that every different j value is given a different processor, right? So in our diagram, it's every vertical strand that is basically sent to a single processor. And notice that in this particular example, while my iteration space is two-dimensional, my processor space is one-dimensional, okay? And this is the maximum rank solution that I could obtain using space partitioning constraints. And this is not surprising because there are data dependencies on one of the dimensions, and so the only dimension that is parallelizable is the other dimension, which is j. So this is my function, and now basically I can do my code generation. The outer loop is going to iterate on P. And what are the minimum and maximum values for P? They are the same as the minimum and maximum values for J, because P equals J. And so I get for P equals 0, P is less than equal to M, P++, and then I just paste the original code as it is, except that I predicate all the statements with the corresponding processor mapping function. So in this case, it's so that basically encoding the fact that only those iterations should execute on this processor which are supposed to execute on this processor. And in this case, the mapping function is P equals J. So I basically have a predicate which says if P equals J, only then execute this statement, which is my S1 statement. So that's that's our simple code generation strategy. And our next step is to tighten the loop bounds. And in this case, basically, I can see that the inner loop is going to execute only once the statement, and all the other kind of M minus, so out of the M plus 1 iterations of the inner loop, M iterations are going to be empty iterations, and only one iteration is going to actually execute the statement, and that iteration is going to be the iteration when J equals P. And so what I can do is I can just eliminate this whole loop and just replace this with J equals P. And I am done, right? And because I've now set J equals P, I don't even need the guard. And now I can just just copy propagate J equals P so that I can just replace J with P everywhere. And now this is what my new code looks like. For P equals 0 to M, for I equals 0 to N, ZIP equals ZI minus 1 P. Notice the difference, the change that I have been able to make using the space partitioning constraints is that the outer loop on I has now become the inner loop on the same variable I, whereas the outer loop has become a loop on the processor variable P. And this is this is important because now what I have done is, because the dimension on which there was a data dependency, that dimension is now the inner loop, and so I have decreased the reuse distance. Moreover, the different iterations of the outer loop are now data independent, and that's coming from our space partitioning constraints, the way we have set it up. Because we had got the solution, we can be sure that the outer loop iterations are data independent. They don't have any data dependencies. So if I was to look at this pictorially, this is my original picture where there are data dependencies that are vertical, but my traversal order is horizontal, and so the outer loop didn't have the outer loop had data dependencies, so the outer loop could not be parallelized. But now I have changed it. Earlier my inner loop was on J and the outer loop was on I. Now my inner loop is on I, so that's now our new x-axis, and the outer loop is on P, and P is just, you can think of P as J. So basically I've just switched, I've just switched the loops, I and J, the inner and outer loops, so that the inner loop has become the outer loop and the outer loop has become the inner loop. And now in this kind of rotation of the axis, what I see is that all my dependency edges are also horizontal, and my traversal order of the loop is also in the same order as the dependency edges. So clearly I have reduced my reuse distance, because anything that I write is just read in the next iteration. Moreover, different iterations of the outer loop are now data independent and they can be parallelized. So each row can be given to a different processor and without any worry of incorrectness. So this kind of parallelism would keep the program correct. Another way to say this is that I have changed the axes. Earlier my axes were P, I, comma J, and so now my new axes are P and I, and just to distinguish from the old I say P and I prime. And the relation between P and I prime and the original axis I and J is given by this matrix. So P equals 0 into I plus 1 into J, in other words P equals J, and I prime equals 1 into I plus 0 into J, in other words I prime equals I. So the I prime is just the same as I, and P is now J, and 0, 1, 1, 0 represents our permutation matrix, which basically decides how we have permuted my axes so that I have better parallelism and locality. So this particular matrix, which basically dictates how the axes should be interchanged, this transformation is also called loop interchange, because I've interchanged the loops. I've made the inner loop the outer loop and the outer loop the inner loop. So this matrix that dictates what this interchange should look like is also called the permutation matrix.